Wave-particle duality. This topic really deserves a lot more discussion, but we're down to the wire here at the end of the semester. So here's one little video dedicated to the topic. We're going to see that it was discovered in the early 20th century that things normally thought of as waves, namely light, behaves like particles in many instances, and things that we normally think of as particles behave like, conversely, waves. Let's take a brief look at the idea that energy and mass are that there's an equivalence between energy and mass, because we're going to need that for the so-called de Broglie formula. So hydrogen fusion, that's the process that powers the sun. And the details of what's going on in there were not worked out, I think, until the 1930s. So Einstein gave us E equals mc squared, but just because we knew that matter and energy were equivalent doesn't mean that people had sorted out the details of the fusion reactions. But the long and short of it is, you take 4 hydrogen nuclei, and those are just protons, deep in the core of the sun, and smash them together to make helium, which has 2 protons and 2 neutrons. And there's a bunch of intermediate steps there that this graphic has left out. Now, I've picked an arbitrary unit of mass here to simplify the numbers. So this is these masses here. They're all 75. They're not in kilograms. They're not in atomic mass units. I picked these numbers because they're accurate but easier to deal with. So if each of these protons has a mass of 75, then when you squish them all together to make a helium nucleus, you would expect that the mass of this helium nucleus would be 300. 75 times 4, 300. But it's actually more like 298. And that may seem trivial, but that 2 parts of mass per 300, or in other words, 1 per 75, or no, 2 per 300 would be 2 parts per 150, ends up releasing an extraordinary amount of energy, something like 1,000,000 times what gets released in your typical chemical reaction. That's a good number to memorize. The typical nuclear reaction releases something like 1,000,000 times the energy of a typical chemical reaction. And you probably know from chemistry that chemical reactions only involve the rearrangement of the electrons around atoms. They don't involve changes in the nuclei of those atoms. Now, how much energy is released? Well, that's what mc squared tells us. Take the so-called mass defects. We lost 2 parts per 300. If you could convert that into kilograms, multiply that by the speed of light squared, you'd get a really big number. So it's kind of fun to think about. If you could just have one of these little fusion reactions happen right in front of your face, like, would you hear it? Would you see it? Would it be hot in front of your face? Like, how much energy are we talking about from a single reaction? I suspect that you would be aware of it. And that is what's powering not only the sun, but also, what do they call these? Thermonuclear bombs. You know, atomic bombs, thermonuclear bombs. They're all nuclear reactions. But I think modern fusion weapons, they're called thermonuclear because first there's a fission reaction. Uranium or plutonium fissions first, which releases a tremendous amount of energy. And that energy is used to make hydrogen hot enough to fuse. And then you get the fusion part, hence the thermonuclear. So that's an uncontrolled nuclear process. But then we also have controlled nuclear reactions in power plants, and that's all fission. There are no fusion power plants, as you're probably aware. That's like the holy grail of energy production. So these are all the, nuclear processes. And again, that wasn't known until less than 100 years ago. The nature of the sun's power source was a mystery for a while, because physicists for a while thought it was some sort of chemical reaction, and they were kind of flabbergasted by the required size of the sun to put out that much light for such a long period of time. Anyway, that's another topic. A moment ago, I pointed out that your typical nuclear reaction releases 1,000,000 times your typical chemical reaction. You can see that just by looking at power plants. So these ominous looking things, these are just the cooling towers. There's nothing nuclear about them. I think the nuclear stuff happens in here. Honestly, I don't know. But over here, we have a more common coal-fired power plant. And I looked up some numbers here. The type of power plant that serves a large city would be something like a gigawatt power plant, something that can put out 1 billion, that's billion with a B, joules every second. Because in a large city, you know, to run everybody's air conditioner, and other appliances, you do need quite a bit of power. So I looked up roughly how many tons of fuel each of these power plants goes through in 1 year if they're putting out an average power of 1 gigawatt. And the numbers are kind of shocking. Now, you have to dig up way more uranium ore than this. I think you have to dig up thousands or hundreds of thousands of tons of fuel, of uranium ore, and then refine it. But once you've enriched it or whatever, gotten it down to the pure stuff that you need for a power plant, you're only talking about 28 tons. Now, that might sound like a lot, 28 tons, because a ton is already 2,000 pounds. But we're talking about an entire year here, and that pales in comparison to the 5 million tons of fuel. I have a hard time conceptualizing that. I've never actually been to a coal-burning power plant and watched the fuel being brought in or the coal being brought in, but it must just be a constant train of that, what do they call it, black gold? No, that's oil. A constant train of coal being shoveled into the boilers to go through that much in a year. This gives you some sense of how much we're talking about. And yet there's a whole lot more. They say there's a lot under the ground within the boundaries of the United States. Okay. Why am I talking about this? So that this relation right here doesn't seem too mysterious to you. So this is something you would have learned if you had read the chapter, or if we had covered the chapter on special relativity, which is an awesome topic. It's not particularly mathematical, believe it or not. There's not a lot of calculus even. I don't think there's any calculus for the treatment that you find in this book. Conceptually, it's challenging. But I like to call this the energy momentum triangle. You see, in 3A, you learned that the energy of a moving particle was 1/2 mv squared. That's the kinetic energy. But hopefully you have some sense from the previous slides that something does not need to be moving in order for it to have energy, because there's energy locked up in the mass even of hydrogen atoms. And when you squash them together to make helium, you lose some of that mass. There's a mass defect, and that mass shows up as energy. So there's a mass energy equivalence. So just by matter being, just by sitting there on a desk, a cup of water has a lot of energy locked up in the mass of the nuclei. And if you could somehow liberate some of that, it's shocking how much energy you could liberate. So that's called the rest energy. That's why I'm talking about this, so you're aware of this quantity, rest energy. Think of M, for instance, as the difference in mass of those 4 hydrogen and then the helium nucleus that they made. If that was M, multiply by c squared to find out how much energy would be released in that fusion reaction. Okay, well, yes, things have rest mass, and in other words, rest energy, mc squared is in joules, but once you get them moving, they have an additional energy that we call kinetic energy, and the total energy of the two is what we call E. E represents the total energy. That's the rest energy, which is not always available. Like, there are ways of getting that rest energy out of uranium atoms, for instance, when you allow them to fission, or hydrogen atoms when you squish them together to make helium, but it's not always accessible. And the other contribution to the total energy comes from the kinetic energy. Now, there's a relation between momentum and kinetic energy. Momentum is mass times velocity, at least classically it is. And kinetic energy is 1/2 mv squared. The fact that they both involve m and v should make it a little more plausible that the energy associated with the kinetic energy, the motion of the particle, has something to do with its momentum. Okay, so I drew a right triangle because everybody knows Pythagorean theorem. If you can remember this triangle, and it's easy, right? PC, just think politically correct, or personal computer, and then mc squared, everybody's heard that. Those are the two sides of your right triangle. The hypotenuse E is the total energy. There it is. It's just like c squared equals a squared plus b squared. Of course, if you want E, not E squared, you'd have to take the square root. But if you know the momentum associated with the particle's motion, and you know its rest mass, then you can find the total energy that the particle has, including its rest energy. Now, we're not going to use rest energy for the end of the semester here. It's not going to be on your exam, but you'll need it to understand what we're going to do here in just a few minutes, or a couple minutes. Less than 1 minute. Yeah, right now, actually. Okay, so a photon, these particles of light, that were first postulated. Whoops, hang on a second. These particles of light that were first postulated by Einstein in order to explain the photoelectric effect. It was discovered very quickly that they don't seem to have any mass. So particles of light are massless. And if that's the case, then m over here is 0, and that term's gone. And then you could just take the square root of both sides, and you would have E equals pc. I think that's worth memorizing, especially if you're going to study more physics. This is the relation between the energy and momentum of a photon, a single particle of light. So it's kind of strange, right? A particle of light, we're saying it has no mass, and yet it has momentum. That's hopefully seems a little odd, because usually when we calculate momentum, it's mass times velocity. How can it have momentum if it has no mass? Well, this was one of the surprises introduced by Einstein. Solve for P. P is E over C. And if that looks familiar, it's because you have seen it before. Think back to chapter 31, early in the semester. We talked about electromagnetic waves. And we talked about the Poynting vector. And remember, the Poynting vector had units of intensity, watts per square meter. And we found that there's a relation between the energy absorbed, or I should say the energy transferred by a beam of light, and the momentum delivered. So don't be confused here. This is P for pressure down here. That's newtons per square meter. This is P for momentum. So this is straight out of chapter 31 in your book. Light can actually impart momentum to something. Remember the example with the little tiny spaceships and the solar sails? If you shine a bright laser beam on those sails, you can actually get the spaceship moving. You can give it momentum by shining a light on it. So in order to figure out the amount of momentum absorbed, all you have to do is take the energy absorbed and divide by C. So in chapter 31, we were not thinking in terms of particles of light. We were thinking in terms of a continuous onslaught of energy brought in by this wave. We thought of light as a wave. So you could just, allow that energy to impinge on something for any amount of time and presumably collect any quantity of energy. But now we're thinking in terms of discrete quanta of light energy. But it's the same relation. You see these two? Here, I'm using P for the momentum of a single photon. This is the quantity of momentum brought in by a beam of light over some time interval, let's say. But now we know that this delta P is probably just the sum of the individual momenta of all the photons that were absorbed. Okay, let's look at the units down here just for review. Intensity is watts per square meter. Well, a watt is a joule per second, and a joule is a Newton meter. So we've got Newton meters, that's joules per second per square meter. That's intensity. And then speed of light has units of meters per second. And you see all this cancels and gives us newtons per square meter, which is indeed the units of pressure. Okay, so this was all known in Maxwell's time. You can manipulate Maxwell's equations and use the 19th century theory of electrodynamics to come up with these relations. This is definitely a modern result that nobody knew about until 1905 or after 1905, because it comes to us from relativity. So these two pieces of the theory are arguably separated by several decades. Okay, I'm going to call this the Planck-Einstein relation. Planck, because Planck's the one who discovered this constant with his investigations of black body radiation, and Einstein because he used this result to very simply explain the photoelectric effect. So this is the energy E of a single photon of frequency F. And now we can put these together. Can we not? Let's see here. Right, because if momentum for a photon is energy over C, let's plop in the Planck-Einstein formula for energy of a photon. Stick that right here. And then do you recognize this? F over C. We've got a wave's frequency and a wave's speed. Well, remember this relation? The speed of a wave is just how many waves go by per second times how long each wavelength is. We learned that early in the semester, and we're talking specifically about E and M waves, which have a very specific speed, or a particular speed, 3 times 10 to the 8th in vacuum. So let's take this and solve it for lambda. The wavelength of an E and M wave is just the speed divided by the frequency. That's what we have here. In the denominator, we've got C over F, which is the same as lambda. So what I've done here is use the fundamental relation for waves, which is speed equals lambda times frequency. And I've also used the formula for the momentum of a photon. Now, that one, you didn't really see where it came from. I just threw it into the slides. You'd have to learn actually even more relativity than is presented in your book. I don't think your book's really going to show you where this comes from. And we put those two together to get this result. So if you'd like to know the momentum of a photon, we're talking about photons here, you take Planck's constant, that's interesting, and divide by the wavelength. So in the 1800s, nobody was talking about the individual particles of light. That's an idea that had fallen out of favor for quite some time, because remember, I think it was 1801 that Thomas Young showed the interference of light in a double slit experiment. So for almost 100 years, people had been fairly convinced that light had wave-like properties. But here we are, just a few years after 1900, talking about the momentum of little packets of light. And to do that, we're using this constant that heretofore nobody knew about. 10 to the negative 34th. Nobody was using that number prior to Mr. Planck, the grumpy guy in the photographs. Okay, so here's our starting point now for a new idea. And let's just get used to thinking of this in a couple different ways. I like to think about it this way. The product of momentum and wavelength is h, so that h is by itself there. Of course, you could also solve this for lambda. So if you happen to know a photon's momentum, then you know its wavelength. And you should really think about that graphically. The more energetic a photon is, the more momentum it has. Because remember, P is equal to E over C. So the more momentum a photon has, the shorter its wavelength is. You just want to have some intuition about that. So the faster this thing squiggles here, the greater the momentum of that photon is. And that doesn't mean it's moving faster. Remember, all photons move at the speed of light. It means that their wavelength is shorter. Now, this is what you might call a wave packet here. I don't want to take too much of a diversion here, but you can actually make this graph by adding together a whole bunch of sine waves of different frequency. We're talking about Fourier transforms. But yeah, you can see how this is flat, and then it starts to oscillate, and then it goes flat again. There is no single sine wave that does that, right? Sine waves oscillate forever in both directions. So if you want to localize your wave, it turns out you have to combine multiple sine waves of different frequencies. And if you really do want it to end and never start to oscillate again as you go off infinitely to the left or the right, then you actually have to add together an infinite number of sine waves. So we're talking about Fourier analysis. Some of you are going to learn about that, especially some of you electrical engineers. But you just want to know that faster squiggles in space means a more energetic photon, or a photon with higher momentum. Okay, so again, here's the double slit experiment. You need coherent light to pass through the double slits. Now we didn't need this in our experiment because we just used a laser beam. Laser beam is already coherent, but 100 years ago, before lasers, you would have had to have a very bright light source here, and then by passing it through a single slit, I believe that's called collimation, then the light that comes out of that single slit is already coherent, much like laser light. Okay, you saw this in lab. Remember, we measured the distance between the fringes, and we measured the distance from the screen to the slits, and used that to calculate the wavelength of the light. That's the distance from crest to crest. That's the famous double slit experiment. Here's a couple different graphics of that. Over here, you can see a graph of the intensity versus position. And do you see how this swells towards the middle and then decays again? That's because this, whoever made this graphic is also accounting for the single slit diffraction profile. Remember, when you pass light through two slits, you're actually seeing the simultaneous action of the interference from the two slits and the diffraction from a single slit. Okay, that's just review. Now, here is a wild topic. Hopefully you've read this already, but how can we do this justice? When we did this in the lab, when we shined the laser light through the double slits and observed the fringes, if you happen to know the power of that laser, and it was probably less than a milliwatt, if you happen to know the power and the frequency, you could easily calculate how many photons were coming out of that laser per second. And it's a really big number. I'm assuming it's a billion trillion or a trillion trillion. And that laser is not particularly bright, but if you had a really controlled lab environment and some fancy expensive equipment, you could probably send light through these slits that was extremely dim, so dim that you might be talking about a single photon per second. Now that can't be easy to achieve. We definitely don't have that kind of equipment in our lab at LBCC, but it has been done. I don't know when this was first done, but this is like old news now. Plenty of people have shined light, coherent light, through 2 slits at a time and had it so dim that 1 photon at a time was being developed on photographic film or detected by a digital camera. And if you don't believe that, let's just look at the graphics. I believe these are actual photographs from such an experiment. This is in your book. So it's very dim light. You wait a little while and you see this. This is, each little dot is where the light exposed the film, let's say. It was probably a digital camera, but suppose you were exposing film the way cameras used to work. The exposure shows up with these little individual points. It's not like the whole screen gradually gets more and more exposed. Okay, if you wait longer, you start to see this. It still looks like a mess, kind of random. I don't really see any structure yet, but very shortly, it starts to become evident that the photons are clustering in bands, and they're not arriving so often in between the bands. If you wait long enough, it becomes very clear. You're looking at interference fringes. Now, if this doesn't shake your confidence and kind of spook you out, it's because you either know about it already, you're not really thinking about it. If 1 photon at a time is passing through the slits. Now, again, this is way abbreviated. You should really read more about this in your book. Maybe do some Googling. It really deserves some deep thought. First of all, what does that even mean? 1 photon at a time is passing through the slits. If a photon is a little packet of energy, it seems to me, well, not anymore because I've studied physics, but it would have seemed to me prior to studying this that the photon's got to go through one slit or the other. You can't, if you had a wall and you drilled 2 holes in the wall a little bit bigger than a baseball and you threw the baseball at the holes, it can't go through both holes at the same time. It's got to go through one. So why should the little packet of light be any different? So supposing each photon goes through one slit or the other, and it's got to pick a place on the screen to land. When you first look at the exposure here, it looks like they've all just landed at random positions. And yet, by the end of the duration here, it's very clear that the photon somehow, quote, I'm doing air quotes, knew not to land here. But they knew that they should land here. How does that work? How does each photon know where to land and where not to land? Because remember, when you shine light through a single slit, you don't get this pattern. You might get the central, remember the diffraction pattern for a single slit, there's that broad central band, but that's not what we're looking at here. This is the characteristic pattern of interference from 2 or more slits. How are we seeing an interference pattern if we're sending 1 photon through at a time? So the modern interpretation is that even that 1 photon has to be represented mathematically as a wave. It moves through space and time as a wave. It's distributed over space. It doesn't actually, it's not localized in space, which is a very strange notion. Because if it's a photon, if it's a little packet of light, we know from the photoelectric effect, the photons appear to be absorbed like particles. So this behavior is very bizarre. Okay, now let's actually watch a video of that. That's better than just photographs. And since this video is a little bit long, I'll put on some music. There's the time over here.
Immortal.
Okay, obviously I skipped around there because that would have taken too long, but pretty awesome that you can very clearly see the interference fringes, despite the fact that these photons were arriving one at a time. So if you're not puzzled by that, give it some more thought. It's not at all consistent with your normal life experience. How is it that something we think of as a particle moves through space as a wave? Is it simultaneously a wave and a particle? Well, that's what they call the duality. It's almost like it's a wave on its way to the screen. It's a wave as it passes through the slits. I would even say that this single photon, it's represented by a wave, and because that wave separates into two waves upon passing through the slits, and then those waves interfere with each other. It's almost like you could say the photon is interfering with itself. So that was one of the major revelations of the early 20th century, that light simultaneously behaves like a wave and a particle. And this is one of the major themes from physics. You've probably heard it before. So which is it? Well, some people would say, I think Richard Feynman said, it's a wave. If you have to pick one, it's a wave. You can still recover the particle aspects of your electron, even with the wave model. But you could also just say it's neither, really. It's neither. Our brains perhaps are not really capable of comprehending what a photon is. I mean, what's its shape? Is it a little cubical thing moving through space? Is it spherical? That little squiggle I showed you and called it a wave packet, does it really look like that? From what I understand, the best understanding you could acquire of the nature of a particle of light and how it interacts with something like an atom, it's all mathematical. That's the farthest you can get. And there's a field of physics or a branch of physics called quantum electrodynamics, quantum field theory. If you want to have as good of an understanding as anybody on planet Earth about the true nature of particles of light or what light is, you're going to have to study those things. I'm not quite there yet, but I guess at some point you just have to accept you can't really know what it's like. It's beyond the domain that's accessible to us completely. Okay, well, so this guy, I can't get closure on how to pronounce this guy's name. I think he was French. Louis was his first name. I've heard de Broglie. Pretty sure that's not it. I've heard some people say de Broglie. That sounds a little better. So I say de Broglie. You can say de Broglie if you want. And he was, I think, a young grad student. This is after World War I. I think he served in World War I. And then afterwards, he's in a graduate program trying to figure out what to do for his thesis. And he had this remarkable insight. It's so simple. He figured, wait a minute. Okay, this thing that we thought was a wave for so long, light. There was all this evidence in the 1800s that light was a wave because it interferes with itself as it goes through the double slit. And we've got this great model from Maxwell's equations. We know it obeys the wave equation. We predicted the existence of waves. We know their speed because we were able to predict that and measure it. All this evidence that light is wave-like. And then suddenly, in 1905, Einstein brilliantly explains the photoelectric effect by treating light as little quanta, little packets of energy. So I guess it's no surprise that in short order, somebody realized, namely this guy, if light behaves or displays that duality, if light can behave like a wave and a particle, then why can't that be true for things that we normally think of as particles? Remember the cathode ray experiments? Everybody was rapidly learning all this stuff about the various rays ejected by things. Like you heat up a piece of metal, apply a voltage, you get these cathode rays, which we now know to be electrons. And then Rutherford was messing around with the alpha rays and the beta rays and the gamma rays. And the alpha rays we now know are helium nuclei. So this guy here was the one who suggested maybe those rays also, even though we've been thinking about them as streams of little particles, maybe they have their own wave-like behavior. So he postulated that this formula that works for photons, remember I spent a few minutes showing where this comes from. I had to use a result from relativity and the fundamental relation for waves, speed equals lambda times frequency. He figured if this works for photons, determining the wavelength of a photon using the momentum of the photon, which is E over C, and E is HF, maybe it works for particles too. I mean, finding the momentum of a particle is easy. It's just mass times velocity. So since we know Planck's constant, why don't we just divide by mv, and that would be the wavelength of an electron, perhaps, or even a neutron, maybe even something bigger. So as I look at this picture here, I'm wondering, what is the wavelength of this guy's hair? That's what I'd like to know. Okay. Well, I really should have inserted a couple more slides here, but as an example, let's look at how to calculate the wavelength of an electron. Now, how do you get an electron moving? You can't pick it up with a pair of tweezers and chuck it the way you would throw like a peanut across the room, because, well, electrons just get absorbed by things. It's too small to pick up with tweezers anyway. But what you could do is heat up, thermionic emission from an electrode, get a piece of metal hot, and electrons are boiled away, so to speak. And then you could use an electric voltage to accelerate it. We already talked about that in the previous video when I defined the electron volt. So basically just apply a voltage between two electrodes and have the electron speed up between the two. So if there's no air drag, no friction, we argue that the energy of the electron is conserved. That's another way of saying that the change in kinetic energy plus the change in electrical potential energy is zero. In other words, the change in those energies is equal and opposite. Well, if you start the electron from rest, then final minus initial is final minus zero. So in other words, the final kinetic energy is just the negative of the change in potential energy. And if you haven't taken 3B, here's where you might want to review my previous video. I talked about this a little bit, but the change in potential energy for a charged particle is merely the charge on the particle times the change in potential, which is what we call voltage. Remember, I talked about how you get a voltage when you have an electric field applied through a distance. It's much like the gravitational field. If you move up or down in the gravitational field, you're experiencing a change in gravitational potential energy. Here we're talking about electrical potential energy. Well, since we're talking about an electron, the charge on the electron is negative E, where E is the fundamental unit of the charge. So negative negative gives us a positive. And since the electron, for typical voltages, the electron's not going too close to the speed of light, which means we can use regular old 1/2 mv squared. If you get too close to the speed of light, 1/2 mv squared is bogus. It vastly underestimates the kinetic energy at speed v. But let's just assume we're dealing with non-relativistic speeds here. So we set the kinetic energy of the particle after having been accelerated through that voltage. We set that equal to the energy associated with the voltage. So a charge E moved through a voltage delta V loses this much electrical potential energy, just like falling through a gravity field, and hence it gains this much kinetic energy. Okay, solve that for V. You get root 2E voltage over M. Should you memorize this? I think it's more important to understand what this means. Well, momentum classically is mass times velocity. Again, if you get too close to the speed of light, you can't use mv for momentum. You need a little correction factor in there. M, see how we have an m upstairs and a root m downstairs. What is m divided by the square root of m? Remember how square roots work? X over the square root of x is the square root of x. So we really have a root m up top. That means we can put everything in the numerator. Here is the momentum of your electron in terms of the mass, the charge, and the voltage through which you accelerated it. And now we can take the momentum. Now that we have an expression for the momentum, we can plug it into the de Broglie formula, the de Broglie relation. This is something you really should have memorized. I would try to memorize this. It's so fundamental from chapter 38. You can determine the wavelength of a particle, whether it's a photon or a material particle like an electron, neutron, etc., by taking h and dividing by the momentum. Now, what kind of a number are we talking about here? Because h is really small, 10 to the negative 34th. What if you had a wavelength of 10 to the negative 34th? Can you do anything with that? What's the smallest thing you can think of? I mean, an atom is 10 to the negative 10th. That's pretty small, but it's nowhere near as small as 10 to the negative 34th. The nucleus of an atom, 10 to the negative 14th. That's still way bigger than 10 to the negative 34th. So to have a wavelength that's anything comparable to, say, the wavelength of light, which is 10 to the negative, fifth? Sixth. Something like 10 to the negative sixth is the wavelength of light. you also need a very small power of 10 in the denominator. And that's typically true because how much momentum can an electron really have? Nothing like the momentum of a person walking down the street because its mass is so small. Okay, take this expression for P, plug it in here, and check that out. Since we know H from Planck's results and the photoelectric effect, remember, we would have measured Planck's constant in the laboratory this semester. We know the mass of an electron, we know its charge. I'm going to plug in a typical laboratory voltage of 1,000 volts, and let's just see what the wavelength is like. Here are those numbers. This is the charge of an electron and a proton. Let's go with 1,000 volts. You can check this on your calculator. I got a really small number, 39 picometers. Remember, micrometer or micrometer is a millionth, nanometer is a billionth, and a picometer is a trillionth. I believe I did that right. Yeah, femtometer is 10 to the negative 15th. So 39 picometers. I love that word. It's like saying a cute little picometer. Okay, well, why is this number useful? We didn't get to cover this, but the coolest lab that we were going to do this semester, at the very end of the semester, would be to shoot a beam of electrons at a little piece of nickel inside a vacuum tube. And just like old TV sets, you know, when you turn on the TV, you can hear that staticky sound. It takes a while for the screen to warm up, and then it kind of fluoresces. There's a coating of something on the inside of that tube that fluoresces when it's struck by high-speed electrons. Believe it or not, there's a piece of metal in the back of the TV, and really high-speed electrons come off and smash into the screen. And you can control the direction of that beam with magnetic fields. It's a pretty brilliant invention, whoever invented the older style of television. What were we talking about here? Right, the lab that we would have done. So these dots here represent the atoms in a crystal of metal. Remember, crystal means a regular arrangement of atoms, not like you can imagine maybe glass is kind of irregular at the submicroscopic level, but an elemental solid might look like this, at least for small portions of it. And we would have shot a beam of electrons at a little piece of metal and then looked at the fluorescent rings of interference that appear on the glass tube within, the metal is located within the glass tube. In any case, we could have measured the interference fringes, much like the double slit experiment, and from that deduced, from the geometry here, we could have deduced the wavelength of those electrons. But then we would go back and confirm that using the de Broglie formula, because in the lab setup, you choose the voltage here. You choose the voltage, you look up the mass of the electron, you look up the charge, we know Planck's constant. So you could theoretically predict the wavelength of your electron based on the voltage applied. And then you could go experimentally measure the wavelength by looking at the interference. So there was a bit of math involved in that lab, but it's awesome because it comes out the way you expect. Your wavelengths agree. And it can't be a coincidence because you're talking about numbers like this, 50 picometers, that's so small. Really cool lab. You walk away really having some sense that electrons do indeed behave like waves. So I'm not going to go into the Bragg diffraction here, but all that stuff we talked about early in the semester, interference, diffraction, all based on the wave model of light, right? Not just light, but primarily light. You can apply that same reasoning, the interference wave model, to electrons and use them to predict things like what I just mentioned, the interference fringes. So it starts to get, you feel like you're going around in circles. It's like, okay, we thought light was a wave. Turns out it sometimes behaves like a particle, for instance, in the photoelectric effect. Also Compton scattering, which I hope you read about in the book. But then these things that we normally think of as particles, like electrons and neutrons, also behave like waves. So diffraction has been observed not only with electrons, not only with neutrons. I think your book points out that as early as the 1980s, they demonstrated diffraction even with helium nuclei, alpha particles. I think they've even gotten interference effect with entire molecules. So H2O, for instance, that probably wasn't the molecule they used, but you know the ball and stick model you may have seen in chemistry. How do you reconcile that with the experimental evidence that you can get molecules like that to act like waves? What? How can a ball and stick If that's really what a molecule looks like, it's like little spheres stuck together with these rods. How on earth is that a wave? So that's kind of what I was getting at earlier. You really can't see it. If that causes you anxiety, because before I went to school for physics, I would hear things like, oh, there's 4 dimensions, space-time. You hear things like 7 dimensions. And I had the sense that because I couldn't see that, I wasn't able to visualize that I was clueless, and I wouldn't be any good at physics because I don't know what they're talking about. Well, you do kind of have to accept at some point that there are things you really cannot visualize. You should try, because you got to have some kind of model in your head in order to make a hypothesis and then go test it. But some things can only be understood mathematically, and even then, So we're getting a little philosophical here, but you kind of need to be once you get to this point in the book. Okay, now very quickly, I'll just remind you, for a multiple slit experiment, if you want constructive interference of the waves that leave the slits, you need the path length difference, which is d sine theta, to be equal to an integer number of wavelengths. Well, let's solve this for m equals 1. Where is the location? At what angle do we get the first interference maximum? Solve for theta 1. You would need the sine of theta 1 to be lambda over d. Now, what if your d here, instead of being 2 slits on a Pascal wheel, the manufacturer, we used their wheels for the lab. What if the slit spacing is as small as the distance between atoms in a metal, like the crystal? That's a much smaller spacing. Well, if that were true, the wavelength of light is very short. It's a half a micrometer. So 0.5 times 10 to the negative 6. Or you could say 500 nanometers. But that's way bigger than the spacing between atoms. So if you try to use visible light to get multiple slit interference by shining that light through a crystal, you're not going to see it, because the very first interference maximum would correspond to a sine ratio of 400 to 0.3. That's not possible, right? That's a number greater than 1. The sine of a real angle has to be less than or equal to 1. So you're not going to see an interference pattern if you shine visible light through a crystal of nickel, for instance, which is what we would have used in the lab. If you want to see that kind of interference, this wavelength would have to be much shorter. Well, if you get any shorter than 400 nanometers, practically you're in the ultraviolet range. So you can't use that. And even ultraviolet, 200 nanometers? That's still way bigger than this. Now, X-rays, if you're talking about a wavelength of 0.1, 0.2 nanometers, now you're talking about X-rays, and those can be produced. But check it out. There's another way to make a wave with a wavelength that short. We already saw it. That was this calculation right here. All you have to do is produce energetic electrons. The more energetic it has, the more energetic it is, the greater its momentum. So the more momentum the electron has, the shorter its wavelength is. You can make very short wave or very short wavelength waves with material particles. You just have to get them going fast. And those can be used to probe the structure of solids, individual atoms. So in your book, in your slideshow, you know what? I think there's a photo at the very beginning of the chapter. I'll pull that up. It's hard to fathom, but this image here, you're looking at the contour of individual atoms, something that probably people did not think possible, 50 years ago. But there's no way to produce an image like this with visible light, because the diameter of an atom is something like 1/10 of a nanometer, 2/10 of a nanometer. But visible light has a wavelength of something like, where's my laser pointer? Oops, what's happening? Wrong direction. Visible light has a wavelength of something like 500 nanometers. And it's a silly idea, but if just draw a wave on your paper, and each wave, think of that as 500 nanometers, and then draw a little feature like inside one of the crests that's 2 nanometers across or 0.2 nanometers across. That's just a little speck compared to one of your waves. So it's almost like the waves just kind of snake around the objects you're trying to look at. How can you make out such small features with a wave that's way bigger than the features? Not possible. If you want to look at features this small, you need something with a really small wavelength. And for that, you could use X-rays, but even better, you would need electrons, hence electron microscopes, right? So you've taken material particles and given them extremely short wavelengths. Now, if the double slit experiment works for photons, because photons exhibit a wave-particle duality, then shouldn't it work perhaps for some other entity that also exhibits wave-particle duality? For instance, electrons. If electrons really do have a wavelength, if they move through space like a wave, then how about you shoot a bunch of electrons at a double slit experiment? Now you can't see electrons as they're moving through space, but you could detect them in a way that you can record the position at which they're absorbed. So these dots, they're telling you right here, the dots show where the electrons are actually detected. And what you could do is, instead of shooting 1,000 electrons per second like a normal current, you could have the current so low that you're just looking at 1 or 2 electrons per second, something to that effect. And it's just like the behavior of the photons. If they're all going one at a time, then classically you would think, well, they've got to pick one slit or the other. And then you wouldn't expect to see an interference pattern, because if each one's going through one slit or the other, then you don't have 2 waves interfering. But if each electron moves through space as a wave and breaks apart on its way through the double slits, becomes 2 slits or 2 waves, and then interferes with itself, so to speak, then you do have interference. It's like, what's interfering? It's not 2 different electrons interfering. It's one wave which represents that electron. And that single wave has diffracted through the 2 slits, and now you've got the overlapping crests and troughs. It's a strange idea, but it's not impossible to conceptualize, because you're familiar with interference patterns. You know how to think about how the amplitudes add together and phase difference and all that. So the last thing here is I'll just put on the music again, and you can just watch how this interference pattern builds up slowly, even though one electron is landing at a time. So ask yourself, how does the electron know that it's supposed to land in the interference maximum and not at the interference minimum? How does it know that? If it's not, the only explanation would be it's that electron is like a wave on its way to the screen. It passes through the slits as a wave, interferes with itself. Oh, wrong one.